Okay, so we are discussing about the training in neural networks. We have discussed like how to train a single neuron. That is a single neuron, how it learns, how it adjusts the error, right? A single neuron is also called as perceptron. So that's what we have discussed. So based on the previous weight, okay, the current weight will be either it will increase or it will decrease. So this is the algorithm, I think at last what we have discussed. So any neural network, what it will do in the sense, initially it will assume some random weights. This you should always remember because the whole our job is finding the weights. So initially it will assign some random weights. With that random weight, for each neuron, the this will be calculated. Okay, sigma wixi will be calculated for every neuron, and accordingly the output y will be decided. Okay, like if it is above a threshold limit, it will be 1 or it will be 0. So here we are considering 0 as the threshold limit. If this value is greater than 1, then it will be 1, otherwise it will be 0. So that is what is called as y, and this y is an observed output for one set of input. We'll have multiple set of inputs. This is for a particular input, this is the output you are getting. So that we are adding to y dash, which is an collection of observed set of inputs. Okay, so once this is done for all the inputs, so x dash represents all the inputs. Once you do this for all the inputs, then y dash will contain, y dash will have all the outputs, all the observed outputs. Okay, so for example, for the first input, I will call input 1 what is O1. Let us call O1 is the observed output. Input 2 what is O2. Input 3 what is O3. Like that, for every input we will have an observed output, and that this entire set is called as y dash bar. Okay, this entire set is called as y dash bar. Okay, here addition means we may not add this really, it is just adding to this set. Okay, right? If we take an average of all the errors, then at that time we will add. Okay, so it is not that we won't add, but in this place it is not mentioning that, it is adding to this set. You can consider this as union. It is similar to union. Okay, if the desired output y matches the observed output y dash bar, then output w dash and exit. Okay, then so we have to compare. So this is y dash, which is the observed output. So there will be y which is the actual output, which is the true output. Okay, or we'll call it as the actual output or true output. Okay, say let us say t1 t2 up to t, and this is the true output. You have to compare these two whether it is equal or not. Most probably it won't equal. If it is equal, then whatever the weights we initially assumed, that is correct, but that will not happen normally, so it won't be equal. So in that case we have to adjust the weight. So how we are going to adjust the weight? For each output y, okay, for each output y belongs to y dash, that is this set, you take the first output. Okay, and for each output y belongs to y dash, do this. If the observed output is y instead of 0, if the observed output, if the observed output of y is 1, if this is 1, if the first output is 1, but in the true output if it is 0, then it means that this should be decreased. Whatever our network is providing, it is of higher, but it should be lowered. So what we do, we perform this. We will decrease the weight. wi is equal to wi minus axi. Okay, so that particular weight we will decrease. If the observed output is 0 but the actual output is 1, in that case it means we are lagging, it should be increased. So in that case what we do is wi is equal to wi plus axi. Like that, we have to adjust the weight for mm, for every input, and accordingly the neural network will learn. So here we are not discussing like how this weight is going to adjust it. We are just saying that adjust, but adjust means it is not randomly adjusting. There should be a process. So so we are not going into the detail of that, but that itself is a very big process, and that is what the entire story of back propagation is. Okay. Here at the top level, we are understanding that yes, this is the observed output and this is the actual output. So my output is not matching with the actual output. So my output should be either increased or it should be decreased. That much we are understanding at the at this level. Okay, I think it's clear. So here we are also using one more parameter along with this. So we are not just saying wi is equal to wi minus xi. We are saying alpha. So alpha is nothing but the learning rate. Okay, alpha is the learning rate. So this is how the things works in the single neuron. So the single layer feed forward neural network, it is also called as ADALine, adaptive linear network element, is also an alternative term for perceptron. So this perceptron. So here we are talking about only one perceptron. So this one perceptron is also, it's otherwise called as ADALM. Okay. Yeah, give me 1 minute. So this single perceptron, this is just another name of single perceptron. It is also called as ADALINE, which is adaptive linear network element. Okay. So if there are 10 neurons in the single layer feed forward neural network to be trained, then we have to iterate the algorithm for each perceptron. So far what we have discussed is for only one perceptron. So in a single layer feed forward neural network, if there are 10 neurons, then whatever the task we did for one neuron, that should be repeated for all the 10 neurons. So this is about single layer feed forward neural network. We have discussed the single layer feed forward neural network by understanding how things works for one neuron. Okay, basically the whole story we have discussed for one neuron. So this you repeat for all the other neurons in the same layer. So that is how things will work in a single layer feed forward neural network. So next what we are going to discuss is training in multi-layer feed forward neural network. How training happens in a multi-layer feed forward neural network. Okay. So here let us assume we have multiple layers. So we have an input layer. So let us assume we have an input layer. We have a hidden layer which we call it as M, and we have an output layer. That is, we have an output layer. Let us call this as N. Okay. So a block diagram and its configuration for a 3-layer multi-layer feed forward neural network of type LMN is shown in the next slide. So L represents the input layer, M represents the hidden layer, and N represents the output layer. So this is the pictorial representation of a multi-layer feed-forward neural network with 3 layers: an input layer, hidden layer, and an output layer. So you can see here in input layer you can have, say we are assuming that in input layer there are L neurons. Okay, in input layer there are L neurons, and in the hidden layer there are M neurons, and in the output layer there are N neurons. Okay, so this is so every neuron of the input layer will be connected with every other neuron in the hidden layer. So here we have various weights. The weights which are between the input layer and the hidden layer, we are representing it as V. Okay, it is represented using the notation V. Okay. So for example, if you see this weight, so this is V11. Okay, this is uh, this weight, the weight from the first neuron to to the first neuron of the input layer to the first neuron of the hidden layer. This is V11. Okay. Next will be V12, V13, so on and so forth. This is a connection between the first neuron and the jth neuron. So that is V1j, V1j. Okay, so on and so forth. V next will be V1j plus 1, V1j plus 2, so on and so forth. The connection between the input layer first neuron and the mth layer of the hidden layer is V1m. Okay, so like that it is represented. That so the point is we are using the notation V to represent the weight between the input layer and the hidden layer. Similarly, to represent the weight between the hidden layer and the output layer, we use the notation W. So the term W is used to represent the weight between the hidden layer and the output layer. Okay. For example, here you can see this is the jth neuron in the hidden layer. So this is connected with every other neuron of the output layer. So this is WJ1. Okay, next will be WJ2, so on and so forth. The jth neuron of the hidden layer connecting with the kth neuron of the output layer, which is WJK. Next will be WJK plus 1, WJK plus 2, so on and so forth. The jth neuron of the hidden layer connecting with the nth neuron of the output layer, which is WJN. Okay, right? So what? So could you tell what will be the size of this matrix V? What will be the size of this V matrix? Yes. What will be the size of the V matrix? How many rows and how many columns it will have? What will be the size of this V matrix? It is connecting the input layer with the hidden layer. What is its size? N. No, matrix means I mean it is how many rows and how many columns. It is connecting what and what? Input and hidden layer. What is the size of this input layer? Input layer contains how many neurons? Input layer here contains how many neurons? Not three, there are many dots. So how many neurons are here? It's not three. What term we are using to refer the number of neurons in the input layer? L neurons. What is the number of neurons in the hidden layer? M. In the output layer? N. So what is the size of this V? V basically it's a matrix. So this V represents all the weight that are connecting between the input layer and the hidden layer. So what should be its size? That's what I'm asking. It is connecting what? Input layer and hidden layer. So its size should be what? Its size, its what's the size of the input layer? So it's so what should be the size of V? It should be L into M. It is connecting this input and the hidden layer. So it is L into M. So here we have L neurons and here you have M neurons. So it will be L into M. It will have L rows and M columns. Okay. Similarly, what will be the size of this W matrix? M cross N. Yes. Okay. So what V represents? What does V represents? V represents what? Is it connection or what? Weight? It represents the weight, all the weights between the connections between input layer and the hidden layer. There are many connections. What is the weight of each of these connections? That is represented as V. So this V matrix will have this many entries. And what W represents? What W represents? What is W? weight of what? Everything is weight. V is also weight. W is also a weight. But what's the difference? V is the weight between input layer and the hidden layer. W represents the weight between what and what? Yeah, W represents the weight between the hidden layer and the output layer, and that is represented by a matrix of size m cross n. Okay. So this is what the input layer, there are L neurons. Okay. So number of neurons. So this symbol represents number of neurons in the first layer. This one represents, this is uh, one represents first layer. Okay, that is n represents the neurons, and this two lines. Okay, this line and this line represents number of neurons in the first layer is L. Okay, number of neurons in the second layer or the hidden layer. Here we have only three layers. The second layer, which is nothing but the hidden layer, is M. Number of neurons in the third layer, which is the output layer, is N. Okay, and in the first layer, what is the, then this F represents what is the activation function which is used in the first layer. Okay, and similarly this represents F, this Fi1. Fi1 represents the activation function used in the first layer. This Fim represents the activation function or the transfer function which is used in the hidden layer. And this Fkm, it represents the activation function or the transfer function that is used in the output layer. Okay. So in the input layer we are using linear activation function. That means we are not using any specific activation function. We are just taking the input and we are checking whether the input is greater than some theta or not, some threshold or not. If the input is greater than some threshold, then this layer will give 1, otherwise it will give 0. That's all, nothing else. No other addition, multiplication, nothing is there, because here there is only, each neuron gets only one input, and that input we are just comparing it with some threshold limit. If it is greater than the threshold limit, we output it as 1, otherwise we output it as 0. So that is what this function does. So it is basically a linear transfer function. Okay. Whereas the activation function used in the hidden layer, in this layer, this activation function is called as a sigmoid activation function or sigmoid transfer function. It is of this form. It is 1 by 1 plus e to the power alpha j ij. Okay. So where alpha j is the learning rate. Okay. Where alpha j, you can call it as the learning rate, and or alpha j is some parameter, and ij is the actual input which is coming here. Okay, ij is the actual input which is coming here. So this actual input for this neuron, if you see, it's not one input, it is many inputs it is getting. Okay, so it is getting input from all the L neurons from the previous layer. So everything will be, so it is basically sigma, all these weights will be multiplied. So here we are calling the weight as Vi, V11, V12, like that. So, okay, so it is sigma Vij. Okay, so it's the multiplication of it's a product of this sum of all these weights. Okay, so take every weight, that is sum of all these weights, take all these weights. Okay, so basically we add all these weights, right, and after that after adding all these weights, we will pass on to this particular function, 1 by 1 plus e to the power minus alpha into ij. Okay, so this is basically a sigmoid transfer function. What a sigmoid function does, previously we have learned. Yeah, so basically it will smoothen the signal. That's the point, right? So here, so it will give value between 0 and 1 or minus 1 and plus 1. So it will give some value. So let us assume between 0 and 1 it gives. Okay, so that is what this function. So please remember all these things because this is a bit lengthy topic. Towards the end we should remember that which layer we are using which transfer function. Okay, so in the input layer we are using linear transfer function. In the hidden layer we are using sigmoid transfer function. In the output layer we are using tan sigmoid transfer function. This also we have discussed already if you could recall. So in the output layer, the transfer function or the activation function that we are using is called as tan sigmoid transfer function, which is of the form e to the power alpha I naught minus e to the power alpha uh, I naught divided by e to the power alpha I naught plus e to the power minus alpha I naught. So this type of function is called as tan sigmoid transfer function. So this is just an assumption. Okay, I mean different neural networks will use a different activation function at different layers. But we are let us for our understanding we are taking this example. Let us assume that the input uses a linear function, the hidden layer uses a sigmoid function, and the output layer uses a tan sigmoid transfer function. Okay. So what is the activation function used in the input layer in our case? Yeah, what is meant by linear transfer function? What it does? Yeah, it checks threshold value. If it is greater than threshold, it is 1. Otherwise, it will be 0. And what is the activation function we are using for the hidden layer? Yeah, and what is the activation function we are using for the output layer? Yes. Okay. So with this understanding, let us try to understand like how training works in multi-layer feed-forward neural network. So our objective is what in this? So our objective is basically to identify all the weights that are corresponding to V matrix and that are corresponding to W matrix, because that is the whole problem, because that is what we don't know. Input is known, and also you know what is the correct output, but the network should be adjusted so that for any input it should automatically give the correct output. So where we are so the parameters that we have to find is the weights, the all the weights corresponding to V and all the weights corresponding to W. Okay, where V represents the weight matrix of this part and W represents the weight matrix of this part. So what is the size of the V matrix? It is L cross M. So that is, it will have L rows and M columns. So this is how you can represent the V matrix: V11, V12 up to V1M, V21, V22, V2M, so on and so forth. VL1, VL2, VLJ, and so on and so forth up to VLM. So this we have to find. Okay. So when the training is done properly, this will have good values. That is, mostly for whatever the values in this matrix, the algorithm should be behaving in a proper way. Similarly, we should find the weight matrix corresponding to W. So W is the set of weights which connects the hidden layer with the output layer. Okay. So one more thing you should remember here. So throughout this discussion, we are going to use three variables: I, J, and K. Okay. I refers to the input layer. I refers to input layer. J refers to the hidden layer, and K refers to the output layer. Okay. So here you can see, here we are saying Vij here. For any unknown value in this V matrix, it is called as Vij. So basically Vij means it is some weight between the input layer and the hidden layer. That is what you should understand. Okay. Whereas if you see the W matrix, in W matrix any unknown value, it is represented as Wjk, where J refers what and K refers the output layer. Yeah, so it means it is it is some weight between the hidden layer and the output layer. Okay, so there are several terminologies you have to remember. Okay, one is L represents number of neurons in the input layer. Okay, M represents number of neurons in the hidden layer. N represents number of neurons in the output layer. And generally we are going to refer I with I will refer the input layer, J will refer the hidden layer, and K will refer the output layer. This IJK will be using in terms of identifying the weights. For number of neurons we will be using this LMN. Okay, and the transfer function or the activation function. The activation function that is used in the input layer is a linear activation function. The activation function that is used in the hidden layer, it is a log sigmoid activation function, and the activation function that is used in the output layer is tan sigmoid activation function. Okay, fine. So the whole learning can be divided into three parts. One is input layer computation, hidden layer computation, and output layer computation. So that is, so basically the weight which is coming out of the input layer, what should be the weight of that, and the weight which is coming out of the hidden layer, what should be the weight of that. Okay, and output layer computation means error. With output layer we can detect the error. Based on this error, we have to update the weights that is coming out of the hidden layer, and also we have to update the weights that is coming out of the input layer. So basically three things we have to do, right? So first is the weight which is coming out of the input layer, that is V matrix should be detected, and then the weight which is coming out of the hidden layer, that is W, should be identified, and then we have to calculate the error. Okay, but actually the reverse way. First we will calculate the error, and then we will update the appropriate weights. One minute. I'm not sure if somebody is waiting or. Okay, fine. So basically it's in the reverse way. First we will detect the error, and then we will back propagate and we will adjust the weights of W, and then we will adjust the weights of V. Okay, but here we are discussing first for input layer. So let us consider the input training data at any instant B, I1, I2, I1, II, IL. Okay, so training data is nothing but input. See what is input? In the previous session I have told you input will be something, say your input have many parameters. Okay, so say x1, x2, xn parameters are there. So maybe this is the first input, we will call it as I1. Instead of I1 you can call it as x1, but here we are using x1, so let us call it as I1 input 1. It may be some value, one different parameters will have different values. Okay, right, 120, 30, 40, 2, I2, 2, 33, 4, I3, 7, 8, 23. This is one input. This is first set of input. Okay, this is another set of input. Like that, how many rows are there in your data set? If you have 1000 rows, then there will be 1000 inputs like that. Okay. So here we are calling it as, yeah. Let us consider the input training data at any instant. That is one input training data. So this is nothing but the training data. So let us consider this as, this is called at any time it is called as I to the power I. Okay, or you can call it as I to the power L or whatever it may be, right? Maybe L, I guess. So I represents input, L represents the number of yeah, L is the number of neurons in the input layer, right? Okay, so at any instant one input you can call it as I11, I1, I21, so on and so forth, I11, IL1. Okay, so that there will be L inputs, right? So this superscript represents this is the first instance, then second instance, third instance, and so on and so forth. Okay, where any instance belongs to the training data. Okay, fine. See, one more thing, in any machine learning, normally first what we do in the sense, probably you may be aware, we divide the data set into training set and test set. Okay, training set and test set or validation set, like that we divide. For example, if your entire data set contains 100 rows, if your entire data set contains 100 rows, there is no hard and fast rule for division, but generally the suggestion is you have to take 80, you have to follow 80 by 20 rule. It says that 80% of the data set you consider as trained data. Remaining 20% you can consider as test data or validation data. Okay. So if your data set contains 1000 rows, then first 800 rows or any 800 rows, it need not be first 800. Randomly we select some 800 rows. Randomly we select 800 rows, and that 800 rows we will treat as trained data. Okay. And remaining 200 data set, remaining 200 rows, we will be calling it as test data set. So based on this training data only, we will be training the neural network. So that means the neural network is trained for this data set. So when will you stop training? Only when it starts giving some good output, then only you will stop training. So after some point of time, surely this network will give good decent output. Then you will stop training. But after stop training, say assume that for this trained data set, your algorithm, whatever the algorithm or adjusting the neural network you are doing, neural network is called as model. So you have to identify the right model. So model means like the neural network should have how many layers, how many hidden layers it should have, each layer how many neurons should be there. All these things are modeling. Okay. So once you identify the right model, say for example your neural network is giving 90% accuracy for training data. But this is only for training data. You cannot declare to the world that my network is giving 90% accuracy. You have to test it with the test data, because your network is trained for this data set, so it is giving. Maybe in different data set it may behave in a different way. So to get the true accuracy, actually you have to check your model on the test data. So when you apply the model for the test data, that is on this model you take one instant of test data and see what is the result. So there are 200 instances available. For all the 200 instances of the test data, one by one you check how my model is responding, how many instances it is predicting correctly, how many instances it is not predicting correctly, that you have to identify. So out of 200, if it identifies x instances correctly, then your accuracy is x by 200. Okay, x by 200 into 100, whatever it may be, in terms of percentage if you want. Okay. So finally, what is the accuracy that you are getting for the test data? That is the true accuracy. Only this accuracy you can tell to the world that I am getting this accuracy. For example, say your algorithm, the model is behaving 90 percentage in a good way, that is, it is predicting correctly for the trained data. But for the test data, its accuracy, if it is 75 percentage, then the actual accuracy of the model is only 75 percentage. Okay. So why I am telling this, in the sense here we are using the term training data. So you should understand what is meant by training data. Training data means nothing but whatever the entire data set we have, we divide it into two parts. One part we call it as trained data, the other part is called as test data. So normally how we do this division, in the sense we follow 80 by 20 rule. We will randomly choose some 80 data points and we will call that as training data. Okay. And the algorithm will be tuned for all the parameters like the weight vector, w vector, v vector, and any other things also. It will be decided based on the input from the training data, right? And based on that, we will stop training only when we are happy with the accuracy. Okay. But that is not the final accuracy. Final accuracy should be identified by checking the performance of the model against the test data. Okay. So could someone say what is meant by training data? What do you understand? What is meant by training data? Yes. Hmm. Hmm. Okay. Then we train network with which data set? Not trained. Training data. With that data only we are training the network. Okay. It's not data. You have to call data set because it's not one data, right? There are many data points available. So the entire data set we divide into two parts. The 80% part is called as training data set, and with training data set only the model will be tuned. How the accuracy of the model is calculated? How we will calculate the accuracy of the model? Which accuracy is the correct accuracy? Is it train accuracy or test accuracy? Test accuracy is the right accuracy. So train accuracy is not the train accuracy is you cannot claim that that is the correct accuracy. Okay. So that's what. So simply how you can understand in the sense, for example, say for example, a student is getting good marks here in ICFI Tech. Okay. Maybe he's getting good marks in ICFI Tech because he knows like how ICFI Tech works, like how all the faculties take the questions. So this environment, he is acquainted with this environment. So he is getting good marks. Say always he gets A grade. Okay. So that doesn't mean that he can tell to the world that I am A grader or I always score this much marks. So you can claim, but then you have to appear for some common test which is conducted throughout the world. Okay, then you can say that yeah, all over the world this is my level. Are you getting the point? So that is the difference between training and testing. Okay. But we anyway training is required. Okay. But training should not be confined to an environment. Whether the training is done properly or not, that is what we by checking it with the uh, test data. Okay, so that's what it says. So consider the outputs of the neuron lying on the input layer are the same with corresponding inputs to the neurons in the hidden layers. Okay, so consider the outputs of the neuron lying on the input layer are the same with the corresponding inputs to neurons in the hidden layer. That is OI is equal to II. The input of the jth neuron in the hidden layer, the input of the jth neuron in the hidden layer can be calculated as follows. See, what is the input for the jth layer, jth neuron in the hidden layer? Say, let us assume this is the hidden layer. Okay, say this is the jth neuron in the hidden layer. Let us call this as OJH, which means it is the jth neuron in the hidden layer. Okay, it's the jth. What should be its input? What will be its input? Its input will be a, what will be its input? Its input its input should come from where? Its input should come from where? Yes. Now hidden layer will get input from which layer? Hidden layer will input layer, right? In input layer, how many neurons we have? L neurons. Okay, so all these L neurons output will be coming to this hidden layer. Okay, but so let us assume the output of the first neuron of the input layer as O1L. Okay, let us assume the output of the second neuron of the input layer as O2L. the output of the third neuron of the input layer is O3L, so on and so forth. The output of the last layer is OLL. Okay, OLL, right? Fine. But is it only the output? What else is there? Is it only the output from these layers, from this input layer is coming as an input to the hidden layer, or something else is also coming? Apart from the output of the previous layer, what else is coming? Is this, are we feeding this output directly here, or something in between is there? What is that? Yeah, weight. So this weight is represented using what? V. Okay, so the first weight will be what? V. Yeah, V1 to which, to jth neuron. V1J, V2J, V3J, V4J. The last one is VLJ. Okay. So now can you tell mathematically what is the input for this layer? Mathematically, what is the input for this layer? O L into plus, yeah, plus V3J, so on and so forth. At last, OLL V VLJ. Good. Okay. So that is what this equation. So the input for, what do you call it? The input for any hidden layer, the input for the jth neuron in the hidden layer. Okay. The input for the, so IJH represents what? IJH, I represents the input, J represents the jth neuron, H represents the hidden layer. The input for the jth neuron in the hidden layer is nothing but this V1J, O1L plus V2J, O2L, so on and so forth. Vij, OJL up to VLJ, VLL. Okay, right? So like this we can calculate the, so this is for the input for the jth layer of the hidden layer. Okay, like that we can calculate for the jth neuron of the hidden layer. Like that we can calculate for all the neurons of the hidden layer. So here j varies from 1 to m. Why m? Because hidden layer contains how many neurons? M neurons. Okay, so it is m, right? So that is what this equation says. So in the matrix representation, we can write, so this is what the actual split up. But in matrix form, we can write this something like this. IH. So IH is I. So yeah. So the input for the hidden layer, you consider only the input for the hidden layer. What is that? Is it I mean, input for the hidden layer alone? What is the size of that? What is the size of that matrix? What is the size? No, no, only no m here. Why are you saying m? L cross? Only input. Only input. It is not L. This is hidden layer. Okay. Hidden layers only input we are talking. Nothing else. Don't mix up with weight. Some say like that it will have I. This is IJH, right? This is one input. So it will have what? I1H. This is the input for the first hidden layer. Okay. Input. I mean, a input for the first neuron of the hidden layer. I2H, input for the second neuron of the hidden layer. I3H, input for the third neuron of the hidden layer, so on and so forth. IMH, input for the mth layer of the hidden layer. So all these inputs, if you take, what is the size? That's what I'm asking. What is the size of that? How many rows it has, this thing? All the input alone, it has how many rows? M rows. Okay, so it is, m. How many column it has? One column. So its size is what? M cross m. So its size is m cross 1. Okay. So this entire thing can be represented like this, I to the power h. So this j we are ignoring because now we are representing this as a matrix. So matrix means, so basically this is a vector, this is not a matrix because there is no, what do you call, it has only rows, there is no columns. Okay, so it is a vector, so it's a vector. So it means it has many entries, right? So there are the j is, the length of the j is equal to m. Okay, so IH is equal to VT. VT is this, all these V1j, V2j, so on and so forth up to Vij. Okay. So this is what? This is weight. This is a matrix. So what is the size of this matrix? V matrix. What's the size of V matrix? L cross M. Good. It is L cross M. Okay. But so yes, it is L cross M. That is fine. So let us keep it L cross M. Then O is output. Okay, O is output of the hidden layer, right? O is the output of the hidden layer. So how many output will be there in O? Sorry, O is the output of the input layer. So this is O1, O1L, O2L, OJL. All these are what? Output from the input layer. So how many neurons are there in the input layer? L neurons. So what is the size of that? What is the, if you take only the output of the input layer, what is the size of that? L into L cross 1. Good, good. This you are understanding, right? What is the output of the, what is the size of the inputs of the hidden layer alone? What is the size of the input of the hidden layer alone? M cross 1. Okay. Similarly, the output, the size of the, all the outputs of the input layer is L cross 1. Okay. So that is what this. Okay. So basically this equation can be simply, it can be written something like this. IH, okay, IH is equal to V into O, V into O, right? Okay. But this V for our we are, to make it mathematically convenient, we are not making it, keeping it as V, we are making it as V power T, that is V transpose. We are transposing this. Actually the size of V is L cross M. So when you transpose it, what will become, what will be its size? M cross L. Okay, so that this you got H, that is IH is what? IH is nothing but the input to the hidden layer. So input to the hidden layer, its size is M cross L. V to the power T, V size is L cross M. So when you transpose it, it is M cross L. O power L, which is nothing but the output from the input layer, its size is I cross L cross 1. Okay. So this can be in a matrix notation, you can just say like this. Okay, but actually this represents this only. Fine. Okay. So 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 this is, see, all these will continue. So here for input layer, what is happening in the input layer? Okay, so IH in the sense, this is what the output, I mean the input to the hidden layer. Okay, what is the input to the hidden layer? That is represented using this equation. Okay, this is what we have calculated in input layer computation. Okay, here input layer in the sense, what is the output that is coming out of the input layer, that is multiplied with the weight, and that is going as an input to the hidden layer. So that is what it is calculated here mathematically. Similarly, next we are going to perform the calculation for the hidden layer computation. So again, let us consider the jth neuron in the hidden layer. Since the output of the input layer's neurons or the input to the jth neuron, all the outputs from the input layer will go as the input for the jth neuron along with the weight. Okay, and the jth neuron follows the log sigmoid transfer function. So again, you should remember what is the transfer function used in the input layer. Yeah, in the hidden layer, In the hidden layer, log sigmoid, and in the output layer we are using tan sigmoid. Okay, so now we are going to calculate the hidden layer computation. So in hidden layer, what is the transfer function we are using? It is a log sigmoid transfer function. Okay, so the output of the jth neuron of the hidden layer, is nothing but it can be represented like this: 1 by 1 plus e to the power minus alpha h into ijh. Okay, so where what is this ijh? So this ijh is nothing but this value for that neuron. Okay, this is what which we have calculated in the previous round. Okay, so this ijh for the jth neuron. So what is this j is going from 1 to m, right? So here also we are calculating the output of the jth neuron. So this is nothing but the ijh represents the input of the jth neuron. Okay, so the activation function is 1 by 1 plus e to the power alpha h into the input of the hidden layer. That's it. Okay, see, this alpha part even you can ignore. Okay, this alpha is, previously we have discussed, if you remember, alpha is used to what? This sigmoid transfer function, it will be something, yeah, control the slope of the curve. How this curve should be like this or it should be like this. Okay, for that only this alpha. So this alpha is also one of the parameter appropriately it should be chosen. Okay, otherwise in all the textbooks or in all the learning tools, this alpha will not be mentioned. Okay, so basically what you should understand in the sense, this is we are, whatever the input which is coming to the hidden layer, okay, that on that we are applying sigmoid function. So what is sigmoid function? 1 by 1 plus e to the power minus x. Okay, here what is x? X is here, in this case, in our case, x is ijh, that is the input to the jth neuron in the hidden layer. Okay. Right, again where j varies from 1 to m, and alpha h is the constant coefficient of the transfer function. It's a constant. Fine. Okay, so this is for one neuron in the hidden layer. Like that, we have how many neurons in the hidden layer? This is m neurons. Okay, so that also will be a vector. So like that, there are m neurons. You don't have just one neuron. You have m neurons. So this is so like that. This is first neuron, second neuron. This is jth neuron. You have mth neuron. Okay. So could you tell what will be this equation? How this equation will look like for the first neuron? 1 by alpha h into what? J is I 1h. Okay. What will be the value for the mth neuron? Yeah. Okay. So that's it. So like that. So this also basically it is a vector. So this vector contains m entries, m cross 1. Okay. So this is how the output layer, I mean the hidden layer computation is mathematically represented. So basically this equation is the key equation. And output layer computation. In output layer, what is the activation function we are using? Yeah, tan sigmoid activation function or transfer function. Okay. So output layer, in output, for the output layer, the weight is represented using W. And what is the size of this matrix? It is m cross k, because we have m neurons in the sorry, it is yeah, it should be m cross n, right? It should be m cross n. Okay, it should be m cross n. Okay, in between you can use k, not lost. Okay, so there are m neurons in the hidden layer and n neurons in the output layer. Okay, so it is m cross n. So I k 0, sorry, I k power o. So what does it mean? So here we are, so this is nothing but the input to the output layer. Okay, what is the input to the output layer? Tell clearly. Let us take one neuron in the output layer. Okay, so this is output layer. Okay, it gets input from where? uh, I mean from how many neurons of the hidden layer? M neurons of the hidden layer, right? All the neurons, from all the neurons it will be getting the input. Okay, is it not only this neuron output, not neuron, apart from neuron output, what else it gets? Weight. Okay, yeah. So let us assume the output of the first neuron of the hidden layer as O1H. Okay, the output of the second neuron of the hidden layer. So this is hidden layer. Its size is young. This is output layer. Okay, in output layer also we have n neurons, but for simplicity we are taking only one neuron and we are understanding mathematically how we can represent. Okay, so this is the output of the first neuron of the hidden layer. This is the output of the second neuron of the hidden layer, so on and so forth. Output of the third neuron of the hidden layer. What will be this last one? Output of the mth neuron of the mth neuron of the hidden layer. Yes, and this weight is what? W1. Let us consider this as kth neuron of the output layer. So it is W1, W1K. This is W2K. This is W3K. So on and so forth. Say this is ith neuron of the uh, ith output of the hidden layer. So this is WK, and the last one will be WMK. So it is K only. It is not N. Okay, because it is connected with what? One neuron, not all neurons. Right? So this is previously I said it is. So this is K. Okay, because here we are not seeing the all the weights. We are discussing the weights that are corresponds to one neuron of the output layer. Okay, so which neuron of the output layer we are concerned? Kth neuron of the output layer. So it is WMK. Okay. So how will you represent this mathematically? What? So this is input to the kth neuron of the output layer. Okay, IKO is input to the input. I is input, K is the neuron. Input to the kth neuron of the output layer can be mathematically represented as what? Yeah, O1H into W1K plus O2H into W2K here plus, well, right here O3H into W3K, so on and so forth up to OMH into WMK. Okay, so that is what this equation. Okay, so we here this W1K is mentioned first and then O is mentioned next. That's it. So this is how we got this equation. Okay, and here K will range from what to what? Like this is one neuron. Like this, how many neurons we have in the output layer? Okay, so K will range from 1 to n, right? Okay, fine. So this is so if you take the input, so this input is what? Is it a matrix or a vector? I mean the output that is coming from the hidden layer, is it a matrix or a vector? The output of the hidden layer, only if you consider vector, what is the size? All these O1, O2 up to OM, what is the size? This one, O1, O2, O3 up to only M into what? M, M cross 1. Okay, so that is what this. So this entire O thing we are representing as O to the power H, and its size is M cross 1. Okay. Similarly, if you see the output of, I mean the input to the output layer, input to the output layer. Okay, all these things. So so this is for kth neuron. Like that, there are n neurons are there. Okay. So what is the size of the input alone? Are you getting the point? Yeah, n plus n cross 1. Okay, so that we got this I O. So this is only for kth neuron. Like that, for all neurons, if you calculate, that will be a vector. So that vector will have how many entries? It will have n entries. So it will have n rows and it will have one column, n cross 1. Okay. So this weight alone, if you see, it is a, again this is a vector, because this weight corresponds to only one neuron. But we have how many neurons like that? N neurons are there. If you combine all these n neurons, okay, then this weight will be a matrix. What will be the size of that matrix? W matrix? M cross n. Okay. So this weight matrix will be m cross n. So that is W. That is W. If you take transpose of that, then what will be its size? N cross m. Okay. So WT, that is transpose, is n cross m. Okay. So that is what we get. Okay. Why we are transposing? See, why we are transposing means, can you, because we want to multiply this weight matrix with O. Can you, this multiplication is possible? This is one matrix and this is another matrix. Is, can we multiply these two matrix? What is the rule for multiplication? What is the, when we can multiply two matrix? What is the condition? The number of columns in the number of columns in the, no, no, tell clearly what should be equal to rows, number of, no, no, which matrix? We have two matrices, right? Which matrix row should be equal to which matrix column? The number of column in the second matrix should be equal to the number of rows in the first matrix. That is the rule, right? Number of columns in the which matrix? First matrix should be equal to the number of rows in the second matrix. Here, if you don't do transform, if you don't do transpose, then what will be this? Say we are doing WT is not done, then what will be this size? Instead of n cross n, m cross n. Okay, this is O is m into 1. So can you multiply these two now? So, yeah, why? Because the, how many columns are, yeah, so yes, we want to make it equal. So for making it equal, what we are doing? We are taking the transpose. Is it clear? Hmm? So if you take W transpose, then this will become n cross m. Okay. So that's the reason for this transpose. Okay. So this is how mathematically the, whatever the output of the what do you call, the input to the output layer is represented mathematically. Okay. Next, see, this is only the input to the output layer. This is input to the output layer. We should also calculate the output from the output layer. So what is the activation function used in the output layer? What is the activation function used in the output layer? Yeah, tan sigmoid transfer function. So that formula you should bring here, because we are using that activation function in the output layer. So if you take any particular neuron, say let us take the kth neuron of the output layer. So here OK represents the kth neuron of the output layer. So what it will output, in the sense it will behave based on the trans sigmoid transfer function. So simply speaking, tan sigmoid transfer function is nothing but e to the power alpha minus e to the power minus alpha divided by e to the power alpha plus e to the power minus alpha. Okay. So alpha, I mean, into x. So where x is the whatever the thing you have. Okay. So this is how the tan sigmoid transfer function is given. Okay. Right. So instead of x, so actual formula is x, but instead of x, what we are doing here is we are taking ik0. What is ik0? Ik0 is nothing but input to the kth neuron output layer. Okay, input to the kth neuron of the output layer. We are calculating what? Output of the kth neuron of the output layer. Okay, so here also you can add a O if you want. Okay, which means what? It is the output of the kth neuron of the output layer. Ik0 represents input to the kth neuron of the output layer. Okay, so this output depends on this input. It depends on this input based on this formula. So e to the power alpha naught, this alpha naught is the constant which we have to choose. E to the power alpha naught into ik naught minus e to the power minus alpha naught into ik naught divided by e to the power alpha naught into ik naught plus e to the power minus alpha naught into ik naught. Okay. So this is for one particular neuron in the output layer, that is kth neuron. So if you calculate similarly for all the neurons, then that will be a vector, and the size of the vector will be, that is, it will have n rows, because the number of neurons in the output layer is n, so it will be n cross 1. Okay. So what will be the output of the first neuron? Hmm. Alpha naught into, yeah, I10. Okay, what is this I10 represents? No, no, this output only we are calculating. Okay, output depends on what? Output depends on input. So this is not 0, this is O. This is O. O represents the output layer. This is I represents the input. Input to the first neuron of the output layer. Okay. Input to the first neuron of the output layer. That's what it represents. Okay. So E alpha naught I1 to the power O minus what? E to the, yeah, I O. Okay, this is O. This is O. So right. Similarly, e to the power alpha not I1O plus e to the power minus alpha not I1O. Okay, right. So see, if I say IJO, what does it mean? How will you read? Hmm. Yeah, input to the jth neuron of the output layer. Okay. So similarly, what will be the last entry? What will be the last entry? INO. Okay. Minus e to the power minus alpha naught INO. How will you read this INO? Yeah, exactly. Okay. So this is what? OKO is what? OKO is what? Output kth neuron of the output layer. Are you getting? output of the kth neuron of the output layer. This is the final output of that kth neuron. So similarly, e to the power alpha naught I k o plus e to the power minus alpha naught I k o. Okay. So basically this entire thing will be a vector of size n cross 1, right? So this is how the output layer computation is done. Okay, with all these equations in hand, now we can learn backpropagation. Okay, so to summarize, we are trying to understand how training will work in a multi-layer feed-forward neural network. Okay. So in a multi-layer feed-forward neural network, we are taking a simple case. That is, we are assuming there are only 3 layers: input layer, hidden layer, and the output layer. And we are assuming that there are L neurons in the input layer, M neurons in the hidden layer, and N neurons in the output layer. So with this assumption, this is the model we are assuming or considering. Okay, so there are totally L neurons in the input layer, M neurons in the hidden layer, and N neurons in the output layer, and the weights that are represented between the input layer and the hidden layer are represented using V vector. So the size of the V vector will be L cross M, and the weights that were between the hidden layer and the output layer, that is represented using W matrix. This is matrix. Okay, and the size of this W matrix will be M cross N. Okay, and the activation function that is used in the input layer, we are assuming it to be an linear activation function. Okay, that is, it just checks all the input, it just checks whether it is greater than some threshold theta or not. If it is greater than the threshold, it will output 1, otherwise it will output 0. And the activation function that is used in the hidden layer, we are considering it as a log sigmoid activation function, which is of this form: 1 by 1 plus e to the power minus x. And the activation function which is used in the output layer, we are considering it to be a tan sigmoid activation function or transfer function, which is of the form e to the power x minus e to the power minus x by e to the power x plus e to the power minus x. These are standard formulas. You should not ask like how we got this. Okay, this is a formula, just you remember. This is log sigmoid means this, tan sigmoid means this. Okay, why this means that will become more mathematical. If you are interested, you can explore. That is available in many sources in internet. Okay, but for our perspective, you should remember these functions. Okay, so the whole story is we should identify this weight, this V matrix and W matrix. Okay, so this V matrix can be represented like this. Okay, V of L comma M, and for the V matrix we use the parameter I and J. So that means I represents input layer and J represents the hidden layer. Okay, so the terms or the variables that we use in the V matrix is I and J. So when you say I and J, it represents the weight between one ith neuron of the input layer and jth neuron of the hidden layer. Okay, so that's the actual meaning. When I say Vij, it means the weight between the ith neuron of the input layer and jth neuron of the hidden layer. Okay. Similarly, the weights that were between the hidden layer and the output layer, that is represented using W matrix. For W matrix, the variable that we use is J and K. So when you say Wjk, it is the weight between the jth neuron of the hidden layer and the kth neuron of the output layer. So that is what this Wjk means. Now to understand how this entire network works for training, one of the core part of the training is backpropagation. So if you want to understand, we have to represent this mathematically, then only we can understand. So what we are doing is we are representing the input layer computation mathematically, hidden layer computation mathematically, and output layer computation mathematically. So if you consider the input part, so as you know, in the input we have L neurons. So that can be represented. So for all the L neurons will be passing on the input. Will be passing different values of input at a different time instance. Okay, that is if you have a data set of 1000, we divide the data set into trained data and test data. Normally we take 80% of the data as trained data and remaining we'll be considering as the test data. Okay, so any instance of a input I is given as I11, I21, so on and so forth, IL1. Okay, why it is up to L? Because there are L neurons. So why there are L neurons? Because our input contains L attributes. Okay, so this is the input at one point of time. Okay, so this whatever the output, so this OI represents what? Output of the input layer. Okay, output of the input layer. Okay, the output of the output of, so this equation what it says in the sense, output of the input layer is same as the input of the input layer. That is what it says. Okay, this equation says that output of the input layer is same as the input of the input layer, because we are using a linear function. Okay, so in a linear function, I said that in a linear function, you can, there are different ways of defining linear function. One way of defining linear function is whatever the input, you just pause it, you don't do anything. That is also a linear function. Okay, so if the input is 1, you just pause it 1. If the input is 0, you just pause it as 0. If the input is 0.5, you just pause it as 0.5. That is also a linear function. Or if you make some, if you keep a threshold and based on that you decide, that is also a linear way. Okay, here we are assuming that we are not even using that theta, we are directly pausing whatever the input, we are pausing. So that is what this says. Are you getting this? So that is what this says. The output of the OI means what? Output of the input layer, output from the input layer. Output from the input layer is same as the input to the input layer. Okay, so what will be the size? How many output will be there in the input layer? There will be, it is basically a vector, and that vector will have how many entries? It will have L entries, because it has, the size is L, so it is L into 1. And what is its input? The input is also same, L into 1. So is this part is clear? So what does this mean? What do you understand? OL equal to IL means, what does it mean? Hmm. Yeah, which means that it is not doing anything, it is just pausing it. Okay, are you following that? It means that the input layer is not doing anything, it is just passing the values, that's all. Okay, so in the input layer, if there are 3 neurons, whatever the value you pass here, whatever the input you give, 1 2 3 means, it will just pass, it is just passing it. So if you just pausing this, then how we will represent mathematically? So output of the, this is input layer, output of the input layer is same as the input. Okay, that is what this says. Okay, now next what we have to calculate, the input to the jth neuron of the hidden layer. So input to the jth neuron of the hidden layer, it includes two things. It includes what? It includes the output of all the neurons of the input layer and the weights. So output of the first neuron of the input layer, output of the second neuron of the input layer, output of the so on and so forth, output of the jth neuron up to output of the nth neuron of the input layer and the respective weights. That is V1j, V2j, so on and so forth, VLJ. Okay, so this is the input to the uh, jth neuron of the hidden layer. Okay, so this is for only one neuron. Like that, there are how many neurons in the hidden layer? There are m neurons in the hidden layer. So this j should go from 1 to m. So that means you can write like this, I can write so many things. Okay, so this is for j, this is for j. So if you so basically this is only one entry in this particular thing. Like that we have m entries, like that we have m entries. So the point is, this is ijh. What will be I1h? I1h will be, I1h is nothing but input to the first layer of the hidden layer. That will be V11, yeah, O1 is it one, is it one or yeah, input to the first layer of the input to the first layer of, input to the first layer of the hidden layer. Okay, it is o O1L. Okay, what is O1L? It is output of the first layer of the input layer, O1I. Okay, this top I represents what? Input layer. Okay, this is I. This I represents input layer. So this is first in output from the first neuron of the input layer. Okay, similarly then what is that? V21 O2I plus what will be the V31 O3I, so on and so forth up to V, yeah, VL1, VL1. Okay, because how many neurons we have in input layer? L neurons. Okay, this is we are considering for the first neuron of the hidden layer, VL1 into O what? OLH, OLI. Okay, so this is for the first neuron, this is for the jth neuron. Like that you can calculate for the mth neuron. IMH is nothing but the what is the input for the mth layer, sorry, what is the input for the mth neuron of the hidden layer? Okay, what will be that? V O1M O1I, V 2M O2I, so on and so forth. V LM OMI. Okay, so if you take all these things, basically it is a matrix. So that matrix, how we can generally represent means we can represent like this IH. This IH is basically a vector. Okay, because this contains only rows, there is no columns. How many rows it has? It has m rows, because this is nothing but input to the hidden layer. How many neurons in the hidden layer? We have m neurons, so m into 1. Okay, and this entire V is a matrix. So what is the size of this matrix? The size of this matrix is L into m. Okay, L into m. So it is L into m, that is the size of this V matrix. And what is O? Again, O is nothing but the output of the hidden layer. Hidden layer O is nothing but the O is nothing but the output of the input layer. Output of the input layer, O to the power I is nothing but the output of the input layer, which contains L neurons. So it is L into 1. But can we multiply this? L into m into L into 1. These two matrices can be multiplied. Okay, so if you want to multiply, what should we do? Transpose. So that we are doing this transpose, V to the power, I mean we are taking transpose of this V vector, so it becomes m cross L. So we do L cross 1. Okay, so that is, so this is how we mathematically represent the computation of input layer. Similarly, this is the mathematical representation of the computation of the hidden layer. The output of the hidden layer, how it is calculated. So this is the input of the hidden layer. Here what we calculated here is the input for the hidden layer. This thing, sorry, this thing. Similarly, we should calculate the output from the hidden layer. Output from the hidden layer, we are using tan, log sigmoid function. So that is 1 by 1 plus e to the power minus x. So that we are representing like this. So output of the jth neuron of the hidden layer is 1 by 1 plus e to the power minus alpha h ijh. Okay. So this is only for the jth neuron. Like that, you have how many neurons in the hidden layer? We have m neurons. So that is basically a vector. Okay. The vector size is m cross 1. So this is how we mathematically represent the computation of the hidden layer. Similarly, for the output layer. So if you take the output layer, what is the input to an kth neuron of the output layer? So it will take input from all the neurons of the hidden layer and its weight. Okay, so input from the first neuron of the hidden layer, input from the second neuron, so on and so forth, like that, mth neuron and the respective weights, w1k, w2k up to wmk. Okay, so again this is only for kth neuron. Like that, you can calculate for the first neuron you can calculate for the jth neuron, like you can calculate for the nth neuron. So basically this is a big matrix. Okay, so this matrix, if you see, this particular thing is a vector. This is a column vector. This is nothing but the input to the kth neuron of the output layer. So output layer contains how many neurons? N neurons. So this vector size is n cross 1, and this W matrix size is m cross n. Okay, and this output layer, output is this is what you call output from the hidden layer. Okay, this is OMH represents, or anything here, it is nothing but the output from the first neuron of the hidden layer, output from the second neuron, output from the mth neuron of the hidden layer. So like that, how many neurons we have in the hidden layer? M neurons. So its size is m cross 1. Okay, again W is m cross n. We cannot multiply m cross n with m cross 1 matrix. So we take this transpose so that we can perform this multiplication. So this is how the input to the output layer is mathematically represented. And next we have to mathematically represent the output of the output layer. For the output of the output layer, we are using tan sigmoid transfer function, which is this. Okay, and this is for only the kth neuron of the output layer. Similarly, we have to do for all the neurons of the output layer, again, which will be a vector, and the size of the vector will be, it will have n rows and 1 column. Okay, so let us stop here for today's session. I want you to go through this properly, and also I have shared some videos for back propagation. Please go through that. I have shared some 4 or 5 videos, but all videos last only for hardly 10 minutes, but you will get rich information on that. Okay, and we'll be having what you call quiz on Saturday, right? See, actually yesterday's class I forgot to record. I told everybody to remind me once, but today I am recording. I will share this, and the class which we conducted on Saturday also I have recorded. That also I will be sharing you. But in between, one class will not be there, that you have to refer the PPTs or anything. If possible, I will record and share, but I cannot assure. Okay. So whatever we have discussed after quiz 3, okay, that will be the portion for Saturday's quiz, which is quiz 4. Fine.